allow me to kind of jump, behind the frontier and think about some of the things that might become interesting in the, in the further future. So I want to talk about fermionic quantum information processing here. And this is very much inspired by some of the work all of you guys have been doing during the last years. So it does involve Rydbergs, even though it's not obvious from the title, but we'll get there. So, but first let me introduce why we want to do fermions in the first place. And I guess the answer is pretty obvious because fermions play an important role in nature, no? So in condensed matter physics, in quantum chemistry, also high energy physics, matter is very often fermionic by nature. So this can be written, for example, in the context of digital quantum simulation by writing down some target Hamiltonian. They often take such a form. So I have fermionic creation and relation operators associated to distinct fermionic modes that I will label ITKL. There's a simple part usually, which is free fermion operations, and then there is a tricky part, which is interactions, generically written like this. And that's the generic Hamiltonian you would write down, for example, for quantum chemistry, but also for condensed matter. So in the standard digital computing paradigm we were talking about these last 2 days, you do encode information in qubits, right? So in the very first step, before actually even thinking about how to tackle a fermionic system, you have to somehow map this information onto qubits. And while this is an ongoing kind of research question by itself, let me introduce the very simple, maybe naive way of doing it. This is the famous Jordan-Wigner transformation, where you represent fermionic creation operators directly by qubit, by spin-on-half creation operators, raising operators. And because fermionic degrees of freedom carry different statistics, you have to introduce these Pauli strings here. And generically, this introduces some kind of overhead in the computation. Okay, so the name of the game is to get rid of this overhead. Okay, so this has been explored in the past already, in particular in the context of quantum chemistry, for calculating binding potentials for molecules, mostly using superconducting qubits and trapped ions. But here we want to take some more different step and change the paradigm completely. And this is the idea of fermionic quantum information processing. And this was formalized first in the early 2000s by Bravi and Kitaev, where they wrote down a different computational model. So you don't kind of process qubit information, but instead you work with fermionic modes. And they showed that these two computational models are, in some sense, well, mathematically speaking, they're equivalent. Okay, so any kind of computation that is possible with qubits can also be achieved with fermionic degrees of freedom. And they showed that this example of a gate set is universal for that. So what you need to do is you need to do operations that couple to the density of fermions. You need to be able to do some kind of tunneling. You need to be able to do density-density interactions of these fermionic modes. And, which is a bit nasty, is you also need this kind of pair creation and annihilation operations. So from a computer science point of view, this is maybe not super exciting because there is no hierarchy in complexity. So these two models of computation, either with qubits or with fermions, they're completely equivalent. Okay? But there is, in general, there is an overhead that comes from this kind of mappings. And as long as, well, it's not settled exactly what this overhead is, there is the option for an advantage when working with fermions when you actually want to realize fermionic models. Okay, and that's the kind of key idea that underlies the rest of the talk. So when you think about neutral atoms, then many of these terms kind of come about more or less naturally. One that's maybe a little bit challenging is this pair creation annihilation process because it violates particle number conservation. So we asked the question, what happens if we just drop this? Okay? Obviously, we lose universality and we also lose some other features. But if you think about the types of models that you're interested in, you actually don't really need particle number. They are particle number conserving, right? So in condensed matter, also in quantum chemistry, the number of fermions is very often conserved. And this again opens the possibility to actually use fermionic atoms to encode fermionic quantum information. Okay? And if you fall asleep during the rest of the talk, that's basically the main message. Okay? Use fermionic atoms to encode fermionic quantum information. Again, to do quantum computing with neutral atoms, I'm preaching to the choir. I don't have to say much here. Also, these two pictures are, I feel, now somewhat outdated even. But well, I don't have to convince you that so far we can use atoms very nicely to encode qubits. We have seen various ways of locally addressing them, do single qubit operations, use Rydberg atoms. Now here's this is a Rydberg workshop, of course. And we've seen these amazing results leading to very high fidelities that are now comparable and competitive with other platforms. And one thing that I want to mention, because it will play an important role throughout the rest of the talk, is this arbitrary connectivity by moving atoms around. Okay, so we'll make heavy use of that in a second. So here's kind of the outline for the rest of the talk. I want to give you an idea, or I would like to ask you of some kind of upgrades to the existing Rydberg tweezer architectures that turn the experiments into genuine fermionic hardware. And I will talk about what this requires, and specifically introduce two types of gates in the basic building blocks that play a role in the rest of the game. The first one is some type of interaction gate that is literally taking all the types of Rydberg interactions that already exist. And the second one is the new thing, which is where the fermionic statistics comes into play. So since these atoms, since they're fermionic and suppose we want to make use of that fermionic statistics, we need to create spatial delocalizations, right? We need to be able to delocalize single particles among different tweezers, let's say. Okay, and that's the new thing I will be discussing. And it turns out that if you have these two ingredients only, there's already a bunch of fermionic kind of subroutines you can compile, genuine fermionic circuits that you can build, that in principle you can use for hopefully more efficient quantum simulations of, let's say, quantum chemistry. Okay, so that's, well, as I said, that's a plan. I'll briefly sketch the type of hardware we have in mind, and then I will jump over to more theory games, talking about the kind of, let's call it fermionic quantum software we can build that leads me to applications. And then I ask you to keep your complaints about this until the experimental challenges session, because this is quite daunting, I think, but let's talk about this later. Okay. So here's the idea, and if you want to know more, you can have a look at the paper we put on the archive recently. As I said, we want to encode fermionic information in fermionic atoms. So think about tweezers, a bunch of them, let's say L of them, and you have n, smaller l, fermionic atoms that you store in those tweezers. And I code so if you want fermionic qubit in the presence or absence of a single particle in each tweezer. Okay, so that encodes my fermionic register, if you want. And then this tunneling gate that I was mentioning before, in general, the most general single particle operation that I can create, that I can realize that kind of delocalizes a particle between two tweezers labeled I and J, takes this form. Okay, so I have some kind of hopping process with an amplitude and a potential phase, and maybe I also pick up a phase shift due to the presence or absence of fermions. So how do I realize this? Well, the first step is actually pretty obvious, I guess, and has already been done experimentally in several experiments. You just take two tweezers, you bring them in a controlled fashion together, such that these traps are not independent anymore, but form some kind of double wall. Then you let the atoms physically tunnel for a while. Well, if there's one, then it may jump over and create a superposition. And then you kind of move them apart again, these two tweezers, ending up with a delocalized fermionic atom sitting, well, in either of them. So that's literally physical tunneling. So maybe if you want to do something like this, you want to use a light alkali atom like lithium, for example. But in the end, this is basically a cheap way of saying, in principle, now you can add optimal control on top of this and ask yourself, what's the ideal, how do I have to calibrate this operation in order to control all these different parameters of my tunneling gate? Okay, so that's one way. Depending on the type of atoms you like, there's also other options. You could also use a somewhat more sophisticated, but maybe in some sense a bit more useful or not, protocol. We can talk about this, that we refer to as a shuttle. So the idea here is to use an alkaline earth atom, something like strontium, and where we make use of the fact that you can create independent optical potentials for the two different states, such that it kind of behaves like two different species in a single atom, right? So the idea here is you create two types of tweezers. One is a kind of storage tweezer, that's where our fermionic register sits. And then there is a second type of tweezers that independently traps say the triplet P0 state, that you move around independently. Okay, and then you can create this gate in a kind of digitized fashion. Okay, so the idea is this. Imagine you want to do this between two tweezers. Then you first have your storage tweezer sitting there. Then you come with a transport tweezer. You go, they have to be matched. So there's several challenges there. Come on top of one of these tweezers. You make a pi pulse. So internally transfer on this clock transition the state, the atom completely from the storage into the transport. And then you physically move this atom to a second tweezer. Make another pulse with the right parameters with internal XYZ operations that actually controls directly these kind of parameters. Then afterwards, so you create this internal superposition, and then you move the kind of half of the superposition physically away and thereby delocalize it. And then if you end up, if you do another pi pulse in the end, you can convince yourself that you actually get exactly this kind of gate. Okay, so that's maybe a bit challenging. But the idea behind all of this is that once you work with fermionic atoms, then these operations will really be fermionic in the sense that these tunneling gates here correspond to creation and elation operators, fermionic. Pauli exclusion principle is naturally implemented. You get all these fermionic statistics hardwired in a sense because you actually use fermionic atoms. Okay, so that's the one ingredient, and that's I think maybe somewhat very challenging, I guess, experimentally, but not so crazy from a theory point of view. And then the one thing I just add on top is any kind of Rydberg gate that you're have so well demonstrated in the last few years, that here translates to just some kind of density interaction of the fermions. For example, in the case of strontium, you could do it by coupling to one of these Rydberg states, as we have seen throughout the last 2 days. Okay, so as I said before, you all complain about how horribly complicated this will be in practice. Let's assume we have something like this. Okay, so what would this be useful for? So let me try to convince you that that might be a useful idea. I will give you 2 examples, and I start with the first application of quantum chemistry. So once again, the type of Hamiltonian we have in mind is a molecular Hamiltonian that can be written something like this. And what we first have to do is now have to come up with a way to use these gates to build routines that are standardly used in quantum algorithms involving these fermionic models. And what people usually very often do is build unitaries that are kind of inspired by the actual Hamiltonians. So this first part of the Hamiltonian is basically covered by these tunneling gates already. The second part of the Hamiltonian is more complicated, right? It's this interacting part. So somehow we have to be able to, in a digital fashion, kind of realize these interactions. And this you can think of as some kind of pair hopping or a pair tunneling, however you want to call it, operations where really 2 fermionic modes, 2 fermions out of modes K and L get annihilated and then are put into 2 new modes I and J. Or if 2 of them are the same, it more looks like a density dependent hopping, right? Where one fermion from K goes to I, depending on the occupation of some intermediate one. And for these 2 examples, we came up with explicit circuit decompositions. So some notation here now. So this tunneling gate I was talking about before, I will denote now in this way. So in the circuit language now, every line corresponds to a fermionic, to one fermionic mode. And then this tunneling gate acts between the 2. And it somehow, it looks very similar to qubit circuits, but it somehow has a different interpretation because all this fermionic statistics is implicit. And then the Rydberg gates we can just denote by some kind of these yellow blocks here. And then you can show that there exists an exact decomposition of this density-assisted hopping in terms of 2 layers of tunneling gates and 2 layers of interaction gates, which is requires you to tune the types of angles that go into this tunneling gate in a certain fashion. So this is actually relatively easy to understand if you write it down. What's a little bit less intuitive, and what we basically found by brute force search, is this decomposition of this genuine kind of scattering gate, which is written out here, and it involves somewhat less obvious angles. The important point here is that in comparison to, let's say, the naive Jordan-Wigner implementation again, if you allow me to move atoms around, as I've assumed anyway, these kind of circuits they scale. They are not dependent on system size. If you had done some Jordan-Wigner encoding, and these 4 modes, I, J, K, L, are somewhere in your register, and you had chosen your Jordan-Wigner string in whatever way, then it in general involves an operation that involves every single qubit of your system. So these circuits will scale very badly with system size. Whereas in this case, because again, these are actual fermions, fermionic statistics is hardwired into the problem, they're literally finite depth and they will remain finite depth. Okay, so that's kind of the advantage and the potential saving that we have here. So what do we do with this? Well, in the near term, we might think about running some kind of variational algorithms, for example, for quantum chemistry. So we build on these types of circuits, prepare a variational ansatz state, measure the energy of this operator in that state and try to minimize the energy to find, for example, the ground state of some molecule. In the context of quantum chemistry, a famous example is so-called unitary coupled cluster ansatz. Basically, you start with a somewhat optimized single particle basis and then act with unitary operations on top that create correlations that come from interactions, basically. So here's one example how such a circuit would look like. It's actually ridiculously short. For an example where you have two fermionic atoms in a system with only 4 modes, and then this type of ansatz actually boils down to just one layer of these tunneling gates and then one layer of this particular interaction gates, which again we have decomposed into these native things. Yes, please.
So maybe it's a stupid question.
Oh.
If you're to do variational approach anyways,
yeah.
Why do we care implementing fermionic gates, but just work with the qubit all the way and only interpret by occupation number at the end?
I don't have a good answer because it's not clear what's the expressivity of these variational circuits. So I agree with you.
So there's no obvious reason.
There is no obvious reason at this point.
Intuitive belief.
It's exactly. There is another case where I think it's more relevant, which is when you, for example, think about real-time evolution, where you actually want to realize operations that come from the Hamiltonians. So for this variational, maybe in that sense not the best example. I agree. I completely agree. Nevertheless, kind of by the usual intuition, they seem to work well. Actually, in this particular example that I showed you, we did this. So this is actually relevant for somewhat trivial molecule formed out of lithium and hydrogen. It's known that this type of ansatz for this particular truncation with only 4 orbitals actually captures the ground state exactly. I mean, this is a stupid toy example, but so in this case, the fermionic statistics in that sense already helps in some sense. So we ran very simple simulations just to check that this works in this case versus some assumed error parameters, basically of the tweezers, so fluctuating positions and frequencies, and showed that in principle we can use this ansatz to find the true ground state. So that's one example. How am I doing time? I lost time at the beginning.
20 minutes.
Oh, good, good. Very good.
I'd say 10 to 15 minutes of questions.
Okay. So let me go to a second example, which is maybe even further behind the frontier, but which is personally very dear to my heart, which is gauge theories. So ultimately, quantum computers might be used to tackle things like quantum chemistry, but actually also we have this vision of solving QCD, okay? Of actually tackling high energy particle physics questions. And these theories are rather complicated. They involve gauge fields coupled to fermionic matter. So the gauge fields by themselves are a completely own story, but also there we have fermionic matter and we have to somehow deal with it. Okay, and that's not so easy how to do. And if you actually look at the first estimates how to do that in a fault-tolerant regime, that's even more crazy than for real quantum chemistry applications. So I think that's one field where in the future quantum computing might actually have an impact. So let me briefly introduce you to some kind of the simplistic version of this, the most simplistic version of this that you can come up with, which is a Z2 lattice gauge theory in 2+1 dimensions. So the key features of a gauge theory are already captured by an Hamiltonian of this type. So you usually have gauge fields in one way or another that live on the links of some lattice. In this case, it's 2D square lattice. And the gauge fields are just represented by qubits. Okay, so just spin 1/2 degrees of freedom. And we also have fermionic matter. The fermionic matter lives on sides of this lattice. Okay, so it's a bit unconventional. In this case, they will just be spinless fermions. Okay, and then the types of Hamiltonian one can write down usually contain 4 different types of terms. There's first this what we call an electric energy term. That's just a single qubit operator on every link. Then there is this infamous plaquette operator. That's exactly what you know probably from the toric code. So that's a 4-body operator that involves 4 qubits around the plaquette in this case. Then there is another term that couples the gauge field to the fermions. So that's kind of the interesting part for today, where a fermion, as one spinless fermion, hops from one side to the next. But the amplitude, again, depends on the state of the qubit, of the gauge field, so to say, in the middle. And finally, there can also be extra, let's call them mass terms for the fermions that in this case just look like staggered chemical potentials. So what makes this theory a gauge theory is the presence of local symmetries. Okay, so there is these operators that I call V that look a bit like star operators you might know from toric code, but in this case they involve not only the 4 qubits surrounding a vertex, but also the fermionic mode in the middle. Okay, so in this case, it's this particular operator that's a product out of 4 sigma x's and this phase depending on the presence or absence of a fermion in the middle here. Okay, and you can convince yourself that this operator for every vertex actually commutes with the Hamiltonian. So there's an extensive number of symmetries, and that's what makes this a gauge theory, and this is what part of the story why this somehow becomes complicated to simulate. Plus it having fermionic matter and so on. And this is why one of the reasons why we looked at this example of strontium before, because you know, well now you know, you can use this as a fermionic register, but you can also operate kind of in the qubit mode by just using different hyperfine states. So here you have the potential to come up with an even more crazy architecture that combines both fermions and qubits in the same atomic species. So you either keep them fixed at these links, or you use this idea of storage and transport tweezers to actually move fermions around between the vertices. And well, I don't want to bore you further with all the details, but here's maybe an example. Oh, Sunwon left. Okay, so you see. Here is an example that might convince Sunwon is that one thing is that we eventually would be interested to simulate processes that happen, for example, at high energy physics colliders. Imagine you actually have a heavy ion collision, and these experiments are rather limited in the sense that they smash things together. In the end, they look what comes out. But there's very interesting non-equilibrium dynamics happening in the middle. And there is no way of simulating this at this point. And eventually, we might try to do that. So for this, we need to evolve in real time. And the simplest way here, again, would be a Trotter decomposition of the evolution. So the question is, can we do Trotter evolution of such a crazy theory? And the answer is yes. And I maybe stop boring you with the details, but collecting some known results from other communities, we can show that with these types of gates that I introduced, so if you look at these circuits, there's these tunneling gates appearing again, and also these Rydberg interaction gates. And this is illustrated here for a case of a single plaquette with 4 fermionic modes. This is the first 4 lines, and then 4 kind of qubit modes. These are the next 4 lines. We can actually write down exact Trotter circuits for the evolution of such complicated Hamiltonians. And once again, the name of the game is here to save resources in the sense that these kind of circuits in principle are independent of system size because the fermionic statistics is hardwired into the problem, and we could in principle scale this up if such an architecture was actually built. Okay, so with that, let's come back to Earth and talk about the challenges and maybe mention the elephant in the room, which is I'm asking you to upgrade your tweezer platforms to include motional degrees of freedom. Well, Manuel actually talked about possible ways to ground state cool by leveraging some of these techniques. But of course, this is also the problem, right? The moment you talk to motional degrees of freedom, you want to control them, you also have to fight against motional decoherence. So that kicks in the very beginning for state preparation. You have to ground state cool the atoms, the fermionic atoms in this case, in the tweezers. So you have to remain in the lowest, or in any fixed actually, motional state of throughout the whole computation. And then you might have problem by scattering light from the tweezers, just heating the system up. Or maybe some of these Rydberg gates that have been built I think they might be rather forgiving to the actual motional degree of freedom because you're not interested in them. Right now, I would be interested in them, so we have to keep this under control on top of the whole thing. And then, of course, when I move atoms around, I have to stay in that motional ground state, and I think this is probably the limiting factor for kind of the clock speed of these things, because moving has to be relatively slow. Something else when I was talking, I was mostly talking about tweezers, and of course tweezers are not all the same, right? They have certain imperfections, so any kind of inhomogeneity here couples to the motional degrees of freedom and then maybe a source of decoherence. There could be ways to go around this by replacing some of these things maybe by optical lattices, which of course much more identical. For example, in Munich, actually people, Jano Bloch and co, are working on something similar, combining these ideas of optical lattices together with tweezers, and we've also heard other ideas. Another thing that we briefly discussed in our paper is to use kind of simple error mitigation schemes. For example, for trap inhomogeneity, also in Misha's group, people have thought about kind of shuffling tweezers around to in a kind of echo ideas cancel out these inhomogeneities to first order. But I think I guess everybody in the room has something else to add to this list. But I hope I've convinced you that it's an intriguing idea in principle to kind of upgrade these platforms to actually use the fermionic statistics as well. Let me briefly comment on what you have maybe already anticipated, my personal taste, where this might go. So we actually have another paper where we push this even a bit further by saying, well, we already thought about fermions, we thought about qubits, maybe we can go even one further step and make it a fermion qubit processor, okay? And actually we showed that this allows, so we had a closer look at the kind of native gates you would need to actually simulate particle physics, which involves more complicated gauge fields, which is where the qubits play a role, also more complicated interactions in general. Maybe a historical anecdote at this point, which is that in the beginning of the building of supercomputers, the actual hardware was actually guided by certain requirements of lattice QCD. So I wouldn't be completely surprised if maybe coming from quantum chemistry or high energy physics, the future of super quantum computers might be guided by some of the actual requirements for some of the really hard problems you want to solve. It doesn't have to be by high energy physics, but I wouldn't be surprised if we should spend some more time of what some people call co-design for the actual problems. Another more near-term thing I think is related to what Sunwan asked, is what's the actual expressivity of variational fermionic circuits? What kind of states can we prepare efficiently? Will they be useful for something? So this needs to be settled also from a theoretical point of view. And then going back to the very first slide, it would be, of course, nice to come back to universal computing. And this requires a way to implement this nasty particle number violating term. We have some ideas here. I'm not yet super convinced, so I would be happy to hear your opinion about that. And then also the question of fault tolerance with these fermionic operations, talking about fermionic error correction is not very much explored at this point. So with this, I'm coming to the end. This was a fun project involving actually a lot of people. I want to point out the leading PIs in Innsbruck. That's of course Peter Zoller and Hannes Pichler. I also want to mention explicitly Daniel Gonzalez-Guarda, who was another postdoc in our group who took the lead in finishing this project. And then we had a lot of kind of experimental support, both from Gila, Adam, Yunye, and of course from Misha's group here in Harvard. So with that, thanks for your attention.
All right. So it's now hardcore participants hall left. Any questions?
Apart from like the difficulty in generating these pairing gates, is there a sense on which they're fundamentally like more complex from the expressivity? Like is it known whether like these pairing gates, like if you increase the number of, for example, if you have a finite amount of pairing gates that you can make, is it known like how much more expressivity you can get? Like how many of these pairing gates you need to get epsilon close to universality, for example, or?
So, I mean, in general, the computational models are equivalent. So there is no kind of, it's not a different complexity class in that sense. Okay, so all savings that you can make will be polynomial at best, which of course in practice can be a lot, but there is no kind of computer science distinction in that sense. Is that part of your question? Because the other part of the question is the actual type of physical state you prepare. No, that's of course very different because many-body systems of qubits have just a tensor product structure, and the many-body Hilbert space of fermions is, of course, it's different. So the type of states are actually physically very distinct.
I was thinking of the other way in terms of like, it seems like because they're so difficult to prepare, it seems like these pairing gates will be like the limiting factor to start off with. So
if you use a naive qubit approach, you mean?
Using the fermionic approach, is it known like how, if I only have access to one pairing gate, I work really hard and I can only do it once with high fidelity, is it known like how much expressivity I gain?
Compared to?
Compared to not having the pairing gate. Maybe we can check.
Yeah, I'm not quite sure how I can give a quantitative answer to this.
But it is like, for example, even this example shows that, somehow these kind of fermionic circuits, they are actually kind of more complex. Like, for example, something like spin echo or something that we take for granted you can do with qubits is much more complicated here, right? Because they these things are kind of non-local, right?
Yeah, fermions are not,
Yeah.
they're intrinsically non-local in that sense. Yeah.
So
Yes, please.
I don't think you're going to calculate something new about QCD with a NISQ era machine, so
I agree.
probably you need error correction.
I
And so
agree.
my question is, does error correction as we know it from qubit world translate here, or do you need to invent some new aspects of error correction or new
So there
approaches
is,
to doing error correction?
so there is a way of kind of mapping everything, but it requires these annoying pair creation gates. So you need to be able to write. So there exist stabilizer codes, for example, but they are made out of Majorana fermions. So you need to have particle number non-conserving terms to apply those ideas.
I mean, this pair creation operation was sort of what we heard about from Tübingen, right? It's this flop-flop. That's the pair
In
creation
principle, yes.
in principle. So, it's known.
But it's not a fermionic pair creation, no?
No,
It's not.
okay,
That's
no.
It's different. No? You could think of a kind of a BCS laser, no? Out of which you take pairs. In principle, at least. Okay.
Guido.
Could you give us a perspective why you would do this instead of saying analog or whatever? Already analog sounds very hard
So
for these lattice gauge theories and etc. Could you tell us why one should do this instead of analog and kind of quantify how hard the tool would be to give you some meaningful results for high energy physics?
So let me give you my personal answer. I spent my PhD trying to do analog simulation of gauge theories. And I think we figured out ways to do abelian gauge theories. If you're a bit more forgiving and ask for the type of gauge theories that are required in condensed matter, then I think you do have a chance for non-abelian. I have not seen a single proposal in the last, basically since this thing started, that convinced me that analog simulation of non-abelian gauge theories is possible at all. So I believe the interactions are so unnatural in AMO systems that it won't happen.
So you're
But
saying that basically this is a way to do that.
Exactly, and digitally I know how to do it. Okay, and that's my personal
It's kind of an analog
point of view.
digital. Okay,
It's kind of,
Oh, yes, but
you.
this is a order of magnitude higher than you probably. So then you get the
Maybe not.
I mean, this is justification. So I would put that as a first slide.
Yeah.
So because otherwise, maybe
No,
becomes
but
tough.
it's, there is a hope that some of these analog digital things we could do much better
Sure,
than
I mean,
digital.
I'm all for this.
I mean, this is analog digital in the sense that the fermions are analog, no? I
Yeah,
mean,
sure. Yeah, it's
so-
kind of a combination of things somehow.
Yeah.
But it's tough. So
yeah.
Going back to the pairing terms,
Yes.
those pairing terms are already in your interactions that you know how to create. So can't you just write some sort of engineering get your pairing terms from the interactions?
Not quite sure if I understand what you said. You mean they're in here because they're not, or is that what you said?
Yeah, for example, here you have in your interactions.
There?
Naturally, you were, for example, talking about how the pairs hopping together, right?
Yes.
Your interactions. So in principle, if you can do some sort of engineering, can't you just get the pairing terms from the interactions?
Not exactly, but in some kind of effective way. If you imagine, for example, building a kind of a BCFS bath or something like that. So we discussed this, but it doesn't, the obvious or the semi-obvious way doesn't seem to scale very favorably, because you need kind of a large bath, because you need to be able to pick out pairs without kind of disturbing the bath. And then, yeah, so this is not completely settled if that's a clever way to do it. But in principle, in this way, you can do it, yes.
I guess this slide, so, guess I think my understanding is classical algorithm is quite advanced for quantum chemistry.
True.
So, I mean, is this the right question to tackle, or is there like something within quantum, like have you talked to quantum chemists to figure out what is sort of the right question to tackle?
So,
Fermionic quantum process.
personally, I have not talked to quantum chemists, but I think this is true for almost any quantum computing application, know that we have to fight against very good classical algorithms. So my personal favorite is always real-time evolution, because there is basically no, no competition.
For strongly correlated, I mean, I think will be very hard to compete with classical algorithms for weakly correlated system or for strongly correlated systems. Yes.
So then the other generic answer I give is always some kind of fermionic systems where quantum Monte Carlo is a sign problem. Say Fermi-Hubbard model at finite doping. There's a kind of equivalent question in high energy physics, which is QCD at finite baryon chemical potential. Well, it's always the same kind of, you have finite fermion density such that all known classical algorithms kind of fail, basically. So I think that's the most promising direction, because we have no competitor, basically. I would say.
Last question.
So I guess we've talked about this multiple times, but maybe because it's interesting. So I guess the kind of like really, really big question, and would be interesting to hear your take again, is like how this compares to just doing it with qubits, and if it's like, if it actually makes sense.
Well, I mean, you're a co-author of this, and we still owe you this answer. And I think before we do a serious error analysis, I cannot give you an answer. So we
so
need.
It's not clear. Is at least one possible conclusion?
It's not clear, and I think part of the problem is that, like, formally these computational models are equivalent, so it will be decided on a case-by-case basis if you actually have some saving. To prove that in general is kind of hard. To prove it in explicit, even in explicit instances, not so obvious to prove it. And then, you, of course, that's more what you're asking, no? Your qubits are so good, and this, what I'm demanding, is probably difficult. You know, how does this compare? And I think for this we need the serious error analysis of such an potential architecture, which is we haven't done yet. I think that's the honest answer.
All right.
It's a cute idea, no? Okay,
Right.
sorry.
Any last minute questions? So if not, you know, I was tasked by Hannes to give a concluding speech. So